Hi, welcome to lecture 13, which is about synchronous counters. Counters. Okay, so before we get into the lecture of designing synchronous counters, let's go over some prep work, introduction, if you will, and talk about in general about counters before we talk about their designs. So, what is a counter? What is a counter? Well, a counter is a sequential circuit which counts. Okay, so the question is counts what? What do we count? And the answer is many things. In counters, actually, they are one of the most used sequential circuits in digital systems. We use them to count events. For instance, um, if you have a sensor and the sensor sending pulses about cars which passes over the highway, those pulses need to go to a counter so that we count the cars. Counters are used to implement timers, and the pulses that are coming from the clock are counted and then translated into some kind of a time interval. So we use them to do some kind of timers and event counters. Okay. Um, And the question then comes, what is the sequence of counting? We count from where to where? Count range, if you will. Typically counters are designed designed using M flip-flops. And let's say for the sake of M here, uh, it could be MGK flip-flops, it could be MT flip-flops, MD flip-flops, whatever type of flip-flops we choose to. So for example, if you have two flip-flops, you can count 0, 1, 2, 3. Can I go above 3? No. So then I go back to 0, 1, 2, 3, 0, and so on and so forth. If I have three flip-flops, okay, I can count 0, 1, 2, 3, 4, 5, 6, 7, then back to 0 and repeat the sequence, so on and so forth. If I have four flip-flops, okay, then I can count 0, 1, 14, 15. Then after that, I go back to 0, 1, and I repeat the sequence. Okay, so you can see that there is this range of counting, okay, from here to here. And this is related to the flip-flop. And we say that if you have M flip-flops, you can count from 0 to 1 to 2, all the way to 2 to the M minus 1, right? And then you go back to 0 and you repeat the sequence from thereafter. Okay, so notice that when m here equals 2, the maximum number is 2 to um, uh, 2, which is 4 minus 1, it is 3. The maximum sequence here, 2 to the 3 minus 1, which is 7. The maximum the maximum number here in the sequence is 2 to the 4, right? Minus 1 equals 15. Okay, so this is basically what the range of a counter. Um, so given number of flip-flops, I can get the range, right? Okay, all right, good. So suppose we need to do the opposite. For example, suppose somebody says, I have a counter which counts from 0 all the way to n. How many flip-flops I need? We say, well, let's say n minus 1. We say that number of flip-flops that you need is log base 2 of n and take the ceiling, right? That gives you number of flip-flops, which is M, that you need in your counter. Recall that we are doing sequential circuits. So flip-flops are essential part of the sequential circuits. So for example, if I am counting events here of 16 event, okay, so number of or 16 codes, number of codes is 16, so I say log of 2 for 16 ceiling, that will be what? 4. This is exactly what I have here. Okay, all right, so okay, so let's talk about another issue for counters in terms of synchronous or synchronization. Okay, synchronization of counters. Counters can be synchronous or asynchronous. Okay, now synchronous counters, it means all flip-flops are connected to single clock. So for example, if you have flip-flops in your design here, this is clock, this is clock, this is clock, okay? All these flip-flops must be connected with single clock. We call this design, so this is for example D and Q, D and Q, D and Q. All these flip-flops are connected to single clock, and we call this a synchronous design. Now asynchronous design on the other part, it's connected to different clocks. So CLK1, which is different than CLK2, which is different than CLK3. Okay, so in this case, watch, these flip-flops are connected to different clocks, so we say that this is asynchronous design because the clocks are not single clock. Okay, so in this course, our emphasis will be synchronous counters. Asynchronous counters are for advanced courses to be covered and discussed. Now, let's go back to the um, counter sequence. Okay, so we say that counters can count, for instance, um, a 0, 1, 2, 3, and then we say that counter 0, 1, 2, 3, and I repeat this. Such counter is referred to as modulo 4. Why modulo 4? Because these 0, 1, 2, 3 are the remainders of any number when I divide by 4. So the modulo operation, so for instance, when you say, for example, what is the modulo of 10, 10 over 4? Well, we say that the when you divide the two, then you get a remainder of 2. Okay, so this is it's probably not a very good example because of the remainder of 2. So that means the modulo operation of 10 mod 4, 10 mod 4 equals 2. Okay, all right, so if we have mod 5 counter, so it will count 0, 1, 2, 3, 4, then 0, 1, 2, so it doesn't exceed 5. Continue, repeat the same sequence. Okay, we will in this so let's talk about a different issue here related to the introduction. Okay, we'll talk about um, the the counters based on their counting. sequence. So we're going to classify now counters. We will classify counters, based on counting sequence. Counting, this is counting sequence or pattern, if you will. And we can say that they could be regular, binary, that is, or irregular. Okay. Now let's see what do we mean by regular and irregular. Okay, so okay, so we probably need this space here. Okay. Okay. Right. So let's see if we can now. Okay. So regular counter can be three types: up counter, down counter, and up and down counter. Irregular, we'll see what they are. So this is one type, another type, and a third type. They differ. Let's classify them say describe them based on special criteria. And the first criteria is the initial state of the counter. Typically, the up counter starts counting from 0. Okay, and the final state, it is 2 to the m minus 1, where m equals number of flip-flops. Okay, so that is the counter. So for example, if m equals 2, then we will count from 0, 1, 2, 3, 0, 1, 2, 3, as we have explained earlier. And then the other criteria is the step. Typically, the step is 1, meaning the next state is described as present state plus 1. Okay. If you have all these features, okay, we say that you have an up counter and it is a regular counter. Okay. So, for example, if you have a counter that counts 0, 1, 2, and 3, we say it's a regular counter. Okay. It's an up regular counter. What about if I have 0, 1, 2, 3, 4? And we said, wait, stop. Because here I'm going to use 3 flip-flops. I should have stayed continued all the way to 7, but now I'm stopping at 4, and then I go back to 0, 0, 1, 2, da 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 da. I'm not using the maximum length or range of the counter because this is not a regular counter. So irregular is a counter which counts not up to the so it might count to 0, 1, 2, 3, 4, and then goes back to 0, da, 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 da. It doesn't go all the way to, it violates this condition. It violates the condition of counting up to 2 to the m minus 1. That is not observed. Another way, if you have a counter that instead of start at 0, it starts at, for example, 1, 2, 3, then it goes 1, 2, 3. The state 0 is missing, so we say this is not a regular counter because it did not start from state 0. Okay, let's say we have a counter which have a step of 2, so 0, 2, 4, da, 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 da. So notice the step here is not 1. Again, we say it's not regular counter because regular counter has a step of 1. Okay. What about if a regular counter has a random pattern? 0, 7, 3, 4. We say, whoa, 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 stop, stop. You don't obey this rule, which is present plus 1. What leads me to the next count? So all of these leads to what? Irregular counter. So regular counter confirms to these rules. And by the way, the up count, we have a down count where I start counting from 2 to the m minus 1, go down to 0. Okay, that's the final state. And I'm going to decrement by minus 1. And next state equals present state minus 1. Okay, now I can have as well up and down counter, a counter which counts out, up, and up. And in this case, I need a control signal. So this control signal, let's say for example x, when x equals 1, 0, then I am an up counter. When x equals 1, then I am a down counter. So and it confirms to the features of the regular counters here. So notice that the control signal is a property of whenever you have a counter which has 2 modes. We don't know which mode we want until we have a control signal that tells us which way we have to go. Okay, so this is the classification. So these are the features 1, 2, 3, 4 of regular counters. If they are violated, they become what? They become irregular counters. Okay, all right. Now, now in the following questions, or in the following in the rest of the lecture, we're going to talk about the counter design. The counter design, and we will talk about regular counters and irregular counters. And for the regular, we'll talk about the up and the down and up and down counter. In all these cases, okay, on all these cases, the 3 cases, we will present 2 design methodologies. One is the general design procedure, which we have learned in the last lecture, because a counter is a sequential circuit, and I can draw the state diagram, the state table, and draw the circuit. So we call this the general design procedure. Then I have simplified design procedure, and basically procedure. Basically, we present some kind of a trick or a quick way to draw the circuit. Okay, so we will do this for the regular counter. Similarly, the irregular, we will design it using the general design design process. Okay, and the simplified design process or procedure. Okay, now, okay, so now in all these cases, it's important in every counter we determine number of flip-flops, and we said number of flip-flops is determined, number of flip-flops, which is m, equals the number of counts that you have, okay, which is, let's say, n, whatever you are counting, okay? Log 2 and take the seeding. It's important you determine always the number of flip-flops, okay? So um, with this right now, we are ready to conduct the next part, which is the synchronous up counter, and we'll leave this for the next recording. Thank you very much.